In recent years, engineered log jams have been deployed successfully in many cases to protect stream banks from erosion, while at the same time they have the benefit of increasing channel complexity and habitat resources. This is the case of a project of the Western Federal Lands to implement engineered log jams at the Hoh River in Washington State. In this presentation, I'll mainly talk about the physical and numerical modeling approaches of the FHWA hydraulics laboratory research to investigate mainly two things. The first one was to investigate the stability of these structures during floods. And the second one was to advance and try to refine the design of engineering log jams that will be used in stream bank stabilization projects. But let's start first with a very brief introduction into the background of the project. So this is the Upper Hoh River, and parallel to that river, there is the Upper Hoh River Road. The Hoh River is in Washington State, as I said before, on the Olympic Peninsula and west slope of the Olympic Mountains in Jefferson County. It's in that one. What happened? Okay. This is actually a fairly big project. So we have 3,200 feet of bank stabilization. The task group decided not to use riprap. They don't want to see any riprap in there. And instead, they wanted to create a habitat, complexity, and natural wood between the road and the river channel. And that's the reason why I decided to use this approach of engineering log jams. And these two pictures basically are showing the problem. This is the Hoh River at two different sections of the river, and the red line that you see in the two pictures is actually the roadway. And you can see that both are located at the outside banks of meander bends of the Hoh River, and that channel migration has reached almost all the way to the valley limits to the north. And basically, this is the main problem. And we are trying to solve it, or the Western Federal Lands wants to use the engineered log jams, but these are not conventional log jams. They are using Dolosse this time. And this is a picture, this is a photo on the left that gives you a good idea of the size of, that's called a deflector log Dolosse bundles, which is basically a 16,000-pound concrete Dolosse that is attached to three 20-foot long logs. And these logs have a diameter in a range between 18 to 36 inch. At this point, I would like to acknowledge the Washington State DOT who came up with this idea of using Dolosse and logs as the main elements or the main components for designing engineered log jams. And they started this project, I think, for the Skagit River that was also located in Washington State. And on the right-hand side, you see basically, as many of you know, the hydraulics lab in McLean, Virginia, has an industrial 3D printer for plastic materials that works 24/7. And we decided to fabricate the Dolosse by ourselves. So basically what we did, we 3D printed molds, plastic molds, to cast about 200 concrete Dolosse. And at the end, we basically just got wood dolls, basically, and tried to keep the same densities that we observed from the field. So basically, we are keeping the same material densities, concrete and wood, which I think this is basically the most important part of the stability of a log jam. Try to balance the buoyancy forces of the wood with this heavy concrete Dolosse. So the model scale is 1 to 25. It was the best suitable model for us to run the experiments in the flume. And this is the initial design of the engineer log jam that was provided by the Western Federal Lands. You will see that the main components are these that we called before in the previous slide, these log Dolosse bundles, and with additional root wads and key Dolosse as well. The key Dolosse are single Dolosse placed. So these are the key Dolosse that are placed basically along the side face of the engineer log jam. So basically, the flow is coming from right to left. This is the length of the log jam, 80 feet by a width of 20 feet. And what you're looking here is the first layer. This is basically the base layer that sits on the stream bed, and the channel bank toe is this line here. This is a side view. You can see here the channel bank slope and the stream bed. So it's basically, this is the layout of the first layer. And for the second layer, these are the components of the first layer. And for the second layer, it was not so clear. It's pretty much a random installation. And also keep in mind, they are just like interlocked. They are just frictionally connected, basically. It's a combination of these Dolosse with some root wads. So this would be the total of elements for the channel bank stabilization project at the Haw River. We are talking about 31 log jams with a total of 2,300 logs, 775 Dolosse, and 450 root wads based on the initial design. And for the flow conditions, in order to run our experiments in the flume, it was very important to consider the fruit similarity. Usually that's the one that we use when we are dealing with free water surface flow. And Western Federal Lands was going to provide the Haw River gradation analysis, like 9 samples. In order to have a look, they also provide the design requirements. So it's a 50-year flood. The 50-year velocity ranges between 12 and 14 feet per second. And the 50-year depth, the design depth, is 15 feet. And you see here on the box, this is the D50 from the Haw River bed. You see there's pretty much a coarse bed material, so between gravel bed and even pebbles. And we run a very quick analysis using the Larson's critical velocity equation in order to check what kind of scour conditions are we expecting in the river. And for most of the cases, we will have like clear water scour conditions, and that's why we decided just to run our experiments in the lab for these scour conditions. These are basically the flow conditions that we use in the flume experiments. And the very important part is that we are always maintaining the same range as in the field. So this is the prototype of fruit numbers, and this is the prototype of the fruit numbers in the lab. Talking more about flow conditions, since this is actually a channel bend, and we have a straight flume in the lab, we wanted to try to basically to test extreme conditions for a straight channel. And we decided to use 2 cases, one using the design velocity as a parallel flow, as you see here, that it's going parallel along the log jams. And the most extreme case, I would say, is like using the design velocity as a perpendicular flow. That's basically going perpendicular straight into the upstream face of the first log jam. And you can see here at cross sections how the velocities are computed. And we're able to also to find some aerial videos that are actually on YouTube from the Washington State DOT of the Skagit River project. And you see here that actually, even as a channel bend, they have also kind of these 2 cases as well. You can find this type of 2 cases. In addition to that, we also wanted to, although the design of the log jam is for partially submerged conditions, the requirements to always have a freeboard above the water surface, but we wanted also to check what happens when the entire log jam gets fully submerged. This is another case that we wanted to see. And this is basically a kind of a summary that I did. The project took over more than a year of running experiments and CFD modeling. The fabrication time was alone, maybe like 2 months. And at the end, we were able to run only scour experiments, which just only focus on scour, how the scour impacts the log jams installations. And that's the reason why we run these experiments on fine sediment. Then once we were confident with the stability of the model against scour conditions, we decided to run also some hydrodynamic loads. We have some load sensors on a single log jam. And based on these two, then we decided to basically we replaced the sediment, the fine sediment by coarse sediment because we wanted to have something similar to the case study. And the advantage of that is that we are now combining these two loads. We are combining hydrodynamic loads with stream stability or stream instability. And the research goals are basically validate the design, develop design coefficients, try to optimize the design, and develop design formulas as well. This is the experimental procedure for scour and stability tests on erodible bed material. Usually, we always start with a laser scan that actually maps the bathymetry, the channel bank geometry, as well as the initial conditions of the log jam installations in the flume. Then we just run the experiment. In this case, we have experiments that runs for equilibrium scour conditions and experiments to see the failure of the log jams. We intentionally wanted to see failure of the log jams in order to basically look for or define for what are those failure modes of the log jams. And at the end of the experiment, we do another scanning to basically run some comparison before and after. And the laser that we use has a very high precision that even if maybe the log jam wouldn't fail, but based on the laser scanning, we will maybe notice that some bundles within the log jam maybe displace a little bit, or maybe they just rotate or turn. That's the advantage of using this system. Okay, for the previous sets, on only looking at the scour, we already found very good findings related to how the scour impacts the log jam installation. And the main one, I would say, was that the key dolosse were actually, once the scour was able to develop along the log jams, basically. So these are the key dolosse. And so for the first case, when the velocity is just parallel to the log jam, the scour hole was just around the key dolosse. But for the second case, the more extreme case, the scour hole was deeper and larger, and that's the reason why we started to see failure of the key dolosse that were just launching into the scour hole. And based on these observations and some other observations, we decided that actually the key dolosse are not providing any stability to the log jam, because also while these key dolosse were just failing, the log jam overall was like stable enough, so nothing really happened. This is just like showing you one of the laser scanning that we do after the test. For this particular case, we basically removed the second layer, the top layer, and we kept the layer A. So these are actually 3 log jam units, and this is the scour bed form around the log jams. For the next step, once we gain some confidence and after doing this new design, that means not using any key dolosse anymore, increasing the elements of bundles for the second layer, which was very important, we decided to run these force measurements where we measure drag, lift, and transverse forces. And at the same time, we run, for the same cases, CFD modeling. Because we wanted to assign a drag force coefficient to this type of structure. And the table shows basically a comparison of the results. This is the drag force measurements for the experiments, and this is the drag force results of the CFD model. The CFD model used a large eddy simulation because we wanted to get the complex flow in detail that's going through the logjam. And you see that they compare really well, actually, and we were able to find a stable drag force coefficient from the experiments and the modeling, which was 1.75. And this is actually very important for us to try to design a stability formulas for the logjam. Based on stability analysis, we were able to get two formulas. One for a fully submerged case, when you have, for a given length, log jam length, what is actually the, no, this is actually for a fully submerged case, what is the minimum required length that will keep the log jam stable. And for a partially submerged case, it's just looking at what is the minimum inundation ratio that we need in order to also make sure that the log jam will stand the flow. And finally, we run the experiments on the coarse bed material, where we can really combine these two loads, the hydrodynamic loads and the stream bed stability, basically channel bank and stream bed stability. And we are looking always at the channel bank stability because the main goal of the logjam is really to protect the channel bank from erosion, as well as the ELJ stability itself. These are the two main goals for these experiments. You have like two images. The one on the left is the partially submerged case, and the one on the right is the fully submerged case. For these two cases, we always use 2 to 3 log jams with a spacing that was also provided by the Western Federal Lands because they wanted to have always, you can ask questions later on to Sven, who is actually in charge of this project, why he considers that it's more beneficial to have always a spacing between the log jams instead of having just like a buffer of log jams installed on the shoreline. Okay, for a partially and fully submerged case, when we have velocities parallel to the log jams, we actually see that, observe that the log jams are very stable. You see just a little bit, this is like an as-built installation, and this is after the scour conditions. You always see that, or we were always able to observe that the channel bank didn't erode at all. You sometimes see some scour on coarse bed material. Of course, it was much lesser than the experience on fine sediment, but the log jams itself, they were always stable. For the case for a partially submerged log jam, but this time the velocity, the design velocity was upstream. We also observed that after just some scour hole, which increased a lot, and some key Dolosse again failing, launching into the scour hole, the log jam itself and the channel bank stability were well maintained. So it was really stable. And for the fully submerged case, which was the most interesting part of this project, is that first we wanted to see failure at some point of the log jam. It was similar to sizing the riprap. So if you want to develop a formula for sizing the riprap, you need to make sure that to find these threshold conditions. And we wanted to do the same thing for the log jams in order to see what is the weak, to find these weak locations. Where do you see the first failure? And I have a recording, which is just like still images. You can see here how the log jam fails. The velocity recorded at this time was 0.92, the design velocity upstream, which was very close based on the stability models that we developed. But of course, we wanted to try to maybe increase the stability upstream because it was always consistent failing in the upstream phase. So this interlocking was not really going all the way down. So the length was not giving, increasing the length was not really so beneficial to the failure upstream. And so we try many things, like in this case, we just fill the first layer with riprap. In the second case, we partially buried the first layer as well. And we also tried to use the key dollars that were not necessary anymore along the logjam, just to try to use the key dollars just on the front face of the logjam. And this is the case where we use the partially buried first layer. And you can see that after the experiments, we reached almost 10%. We went 10% above the velocity, the design velocity, and the logjams were stable enough. But the problem that we observed was that the channel bank was not stable. So from some videos and from velocity measurements, we noticed that once the logjam gets fully submerged, there are some highly turbulent structures above and in between the logjam and the channel bank that creates this erosion here on the channel bank. And finally, I have a summary of the observations and measurements from the experiments. Basically, the first one is that for the fully submerged case, these high velocities and turbulent structures above and around the logjam cause the channel bank to erode. For the fully submerged conditions and design velocity in the approach flow, so the logjam showed to be not to protect the channel really well, and it's because of the first paragraph here. For the other cases, the logjams demonstrated a good stability, and the connection seems to be very reliable. So we always try for design conditions, they always need to try to maintain these densities or this number of bundles for the layer A and also for the top layer. And the key dollars installed at the upstream, which I don't have the results here, this was the third case. They also work very well in maintaining the upstream phase really stable against these high velocities. And that's what I have, yeah. Yes. The moisture, okay. The moisture turned to be important, you're right, because the first experiments that we did when we have only dry wood, the dollars or the bundles were not so stable. Once they were basically saturated, fully saturated with water, they became more stable. But you always need to look for these low flow seasons and high flow seasons, how this is going to play around. Yeah, it's a good point, yeah, to consider. Mm-hmm. Exactly, yes. Mm-hmm. Yeah. Which is kind of beneficial for the logjam stability, I would say, if the weight increases, or if the weight of the wood increases, yes. No, these logs are actually just trees that will just cut, fall down and cut, and will be connected to the dollar. So these real logs are really like trees from that area in Washington State. Yes. Mm-hmm. Okay. You mean that maybe would rot the wood in time? That's okay. That's a good point to consider. Yes. Thank you. Thank you.